My name is AHMAD al-SHAMMARI. I'm the Pipesim product champion in SHAMMARI. Today, I'll be glad to share with you a workshop talking about Pipesim and going to show you also live demo on how to do things in Pipesim. This workshop is going to be 3 hours, and we're going to have a break in the middle for probably 10-15 minutes. And at the end, we'll open the floor for questions for about maybe 15 minutes also. So as you all know, it's going to be a long session. So in order for this session to be fruitful and interactive, I prefer that you type your questions in the chat, and whenever we have time, we can look into them at the end, because I believe there is a good number of attendees right now, and we are live. So in order for us to utilize the time at its best, let's delay the questions until the end, okay? So Pipesim, what is Pipesim? I've already posted several videos on YouTube, as well as there are some videos on SHAMMARI official website on YouTube talking about Pipesim. And some of the slides I'll be talking about right now, or I will show right now, probably is already are already been shared in or presented before. If you're seeing them for the first time, then this is the right place to do so. So what is really Pipesim? So Pipesim is a steady-state multi-phase flow simulator that has been under development for maybe 30 years. Okay. Initially, the first version that was released in 1984 was only what we call keyword driven, right? In which you write your program file in text, and then the software or the program will compile it and will run it and give you the results. There was no graphical user interface. In 1993, the first generation of the graphical user interface came to the industry, and initially it was 16-bit. And then the second generation of the graphical user interface was in 2001, and it was 32-bit. We probably hide this. And in 2015, we came up with what we call the next generation Pipesim, or the new generation graphical user interface, which has been 64-bit starting 2015, and even this one is still under development. And every year we create a new release that will add functionalities and improve the performance of the software, etc. Okay. So even this year we are also adding new functionalities to Pipesim. We are excited about the functionalities that we're adding this year. And I will talk about this in the last slide of this presentation. So Pipesim, as I said, is a multi-phase flow simulator in wells and pipeline networks. And as you may know, there are already similar or competitor software in the market today that can do pretty much, or can perform in the same domain of steady-state multi-phase flow simulators. However, there are certain unique functionalities and capabilities that we believe Pipesim, is better, and these functionalities will probably make Pipesim unique, and that's why we believe Pipesim is the best multi-phase flow simulator in the industry today, from our point of view, of course. But what are these unique features? So, number one, integrated wells and network modeling using state-of-the-art user interface technologies, okay? And when we say integrated wells and network modeling, that means you don't need a separate software for the wells and another software for the network. And then if you want to link them together, then you will need to use lift curves or VLP curves or whatsoever, which will require interpolation at the end. Pipesim doesn't have that. Pipesim can, if you want, can work using what we call well curves, but in the natural or in the basic calculation in the network, you model the wells and the network in the same model, and you add all the granularity of the wells, including if you have multiple completions, horizontal wells, whatsoever, all the equipment in the well, in addition to all the details of the network, okay? And you solve all the system together, and you can switch between wells and networks automatically. I will talk about almost each of these bullets in a separate slide. We have superior network solver, which scales up efficiently for large and complex networks. We have what we call the GIS, or Geographic Information Systems Network Canvas, that can be used for building large networks automatically, digitize pipeline elevations, and visualize pipeline networks. And this, we believe, is very, very useful, and it is only available in Pipesim today, in terms of the basically steady-state flow simulator and then simulation software. And then I'm going also to talk about this later. We have a web-based version and cloud-enabled engine. So if you are in a company where you don't want to install the software in your local PC, you can subscribe to what we call Delphi in Schlumberger, which is the cloud-based environment in which you can access the full-fledged software as if you are running it locally in your PC, but it is running as a virtual machine in the cloud. And if you want to have digital oil field deployment, then we have an engine that can be scaled up in the cloud efficiently to basically run many thousands of simulations at the same time. We have prediction of solids formation risks like scale, hydrate, and wax, and asphaltene. And I'm emphasizing that we are predicting the risk of these formations. We are not predicting the accumulation with time of these solids, because, as you know, Pipesim is a steady-state simulator and not transient or dynamic. We have state-of-the-art corrosion risk modeling using a trusted pipeline advisor corrosion model. This is a corrosion model that has been added recently to Pipesim, and we believe that this is one of the best corrosion models in the industry today. And at the end, we have Schlumberger technical support at your doorstep. We have a huge professional staff that are, or a huge, let's say, number of professional staff that are distributed around the world. In each country, almost each country, we have local professionals and engineers who are experts in our software and experts in the domain that can help you perform your studies and accomplish the best, I would say, projects utilizing Schlumberger software. So, focusing about the main functionalities in Pipesim, number one, we have Olga-S mechanistic flow model. We have advanced PVT and fluid modeling. We have detailed heat transfer calculation. We have integrated wells and network modeling or network simulation, comprehensive well modeling, integrated GIS pipeline profiles. And again, GIS stands for Graphical Information Systems, network of production optimization. And finally, we have what we call the extensibility and automation, in which you can interact with the software without opening the user interface. Let's talk a little bit about each of these functionalities. So number one, Pipesim has the, in terms of the flow model or the pressure drop model, Pipesim has in its core Olga-S flow model, which is the industry standard multiphase flow model that we believe is the best in the industry for multiphase flow modeling. Olga-S, has been a result of more than $150 million of investment in Norway, mainly. Sintef and IFE are research centers here in Norway for multiphase flow. We have also advanced fluid modeling that can be integrated with Pipesim natively, meaning you can actually select these engines, one of these engines that will run with Pipesim without the need to create flow tables, PVT tables and so on. You can perform flashing interactively in Pipesim. If you have a compositional fluid that you would like to model in Pipesim, you can add the components and then you can perform. Pipesim will create the phase diagram for you natively in Pipesim. We have several fluid characterization packages. Multiflash has been with Pipesim for many years from KBC. And when you install Pipesim, Multiflash comes with it. Of course, you will need a separate license for it. We also have a fluid engine that's being added to Pipesim from Symmetry. So Symmetry is a product which is Schlumberger's answer for process simulation. So in process simulation, Schlumberger offers Symmetry, which is a product from a company called VMG that was acquired by Schlumberger about 2-3 years ago. We are now integrating a Symmetry fluid engine into Pipesim. So this is just another option for you as a client if you want to use, in addition to Multiflash, probably for comparison or for certain areas. We believe that Symmetry is strong in heavy oil and in CO2 modeling. Symmetry provides the CO2 solid line on top of the phase diagram, in addition to other strong features. We also have Eclipse 300 as a fluid engine that's also integrated with Pipesim. And also we have GIRG 2008, which is used for mainly single component, again, CO2 and other single component systems. As I mentioned earlier, Pipesim can, is able to also predict potential solids such as asphaltene, wax, hydrate, and scale. And as I said before, we don't predict how much of these solids will form over time, because Pipesim is a steady state simulator. What we do here in these solids, we create the potential risk. We create the line that, let's say, the asphaltene envelope, the wax line, the hydrate line, and we will overlay the fluid conditions over these risk lines, and then you can, based on this, you can predict whether you are exceeding or you are within the risk range of forming these solids. For scale, Pipesim can model a scale concentration or predict solid or scale concentration by using a PVT file created from Scale Chem, which is a software from OLI. For that, you will need to purchase your own license from OLI, create this PVT file, import it to Pipesim, and then Pipesim will be able to predict scale deposition for you. Pipesim also has a detailed heat transfer in which it actually solves the complete energy equation, rigorous thermodynamics, conduction, and convection. Pipesim for the surface pipelines has a rigorous buried pipe model developed by Schlumberger. We also predict the temperature gradient based on heat transfer mechanism. And we last year added RAINY model for wells to consider well bore, material annulus, and ground conductivity. Now, talking more about the practical aspect of the software. I mentioned this before, but I'd like to emphasize this functionality. Pipesim is powerful in the two sides of the production system. It is strong in the pipeline network for flow assurance studies, including surface compressors, for example. Using the GIS, you can capture all the pipeline elevations, but at the same time, you can model the well with its own granularity, with all the details, with all the calculations within the same model. And you can switch from the wells and the network easily by just click of a button, okay? So Pipesim enables modeling of the entire production injection system including wells and pipeline networks in a single file. Simulation solves the integrated model starting from the reservoir boundary conditions until the gathering point. So the system is integrated, in which all the well details, even if you have heat transfer calculation in the well or materials, if you have multi-layer, if you have artificial lift equipment, for all the wells, okay, all this can be solved in one file. This also helps in simple model management, and Pipesim is known to have relatively small file size compared with competitors. An example, for example, you can have 500 wells with all pipelines, okay, with all the details of the wells in one file that is almost 2 megabyte of size. And people who are using competitor software know what I'm talking about, and know the dilemma when you have such a huge network with this number of wells. What's the size of the network that will be needed? Navigation from well to network perspective to perform relevant tasks easily. So in the same file, you can switch to the well canvas or the well perspective, and you can run all the simulation tasks for that particular well without actually changing the network or without touching the network simulation. You can perform the nodal analysis, what we call the PT profile, or the system performance task, or any other. You can install an ESP, design a gas lift system for that particular well, and then you switch back to the network and run the network simulation, okay? And focusing on wells, Pipesim has really strong and comprehensive well modeling capabilities. We have several well-centric simulation tasks, such as nodal analysis, PT profile, and system analysis. In a while, I'm going to really open the user interface and show you all these tasks in practice. We have advanced user-friendly gas lift and ESP design capabilities. We consider multi-pointing and throttling of gas lift valves in conventional well performance simulation. We have comprehensive IPR models, including trilinear IPR for unconventional reservoirs that can go up to micro-Darcy permeability reservoirs, okay? The GIS integration is another powerful and unique capability of Pipesim. You can, model the flow lines. You can capture the pipeline elevations. You can, if you have in your company, for example, if you have a GIS team or Geographic Information Systems team, where they are responsible of generating maps for the fields, right? They will have access to what is called shape files. The shape files are 2D plots that represent the pipeline topology, okay? And these are stored in a small file called .chp. It's a shapefile. These shapefiles can be easily imported into Pipesim, and then this will help you automatically build pipeline networks without going and creating these pipelines. And then with another click of a button, you can capture the pipeline elevation from the graphical or geographical information system services. Pipesim is connected with Esri and other GIS service providers, in which, based on the location of the pipelines or the wells, Pipesim will be able to automatically capture this elevation and create your pipeline automatically for you. Once you are done that, once your network is created, when you run your network simulation, you can visualize the color coding of all the results, including pressure, temperature, flow rate, phase diagram, phase ratios, literally everything, corrosion rate, and so on. And this will help you pinpoint problems immediately on the GIS map. Okay. And of course, if you this is very useful if you have, for example, you want to add a new well or a new pipeline, and you'd like to avoid some earth, let's say, topology, or let's say maybe you have a mountain or a valley or a river, or you have residential area, and you'd like really to digitize the pipeline profile or pipeline location. By avoiding these limitations, you can do that because they are visual, they are in front of you, and then you can, by clicking, it will automatically create the pipeline for you, and then it will automatically, as I said, capture its elevation and calculate its length without the need that you go and enter these details. And I will show you that also later. We have also Pipesim network optimization, in which you can, predict the best, optimization scenarios for your system. You can maximize production. You can distribute the right amount of artificial lift quantities, such as pumping power or gas lift rate, into all the wells automatically. And you can calculate the optimum choke settings for all the wells, okay, by and you can put constraints, like, for example, you want to you don't want to exceed water production by certain amount, or you have a fixed amount of gas lift injection, total gas lift injection rate, and you want to distribute that automatically. And to maximize production or minimize water production, like, for example, it will automatically go to the wells with higher water cut, and then it will give them lower artificial quantity, or it will choke these wells more, so that it will reduce the water production, for example. Many combinations you can add with the network optimizer. And just if you're interested in the network optimization in particular, there is a previous webinar that I've done, I think in 2019 or 2020. It's available on the internet, and it's available on SHAMMARI website. It's probably 40 minutes just talking about the network optimization. Okay. Before we go to the final slide, let's talk about extensibility and automation. So if you like programming, many of the young engineers now like programming, and especially they like Python. You can build and update models automatically using Python scripts, and you can run batch simulations and analyze the results. And a Python toolkit is suitable for all users with basic Python experience. And the Python toolkit is actually embedded within all the variables. So it's not like you have a wrapper a Python wrapper that will run on top of another layer. No, Python toolkit is actually embedded within Pipesim. So all the variables are actually Python variables, and you can, by doing the automatic calculations and so on, you can capture the results, and you can visualize it and create your own digital twin, for example. Again, for the Python toolkit, we have also I think so far we have 2 dedicated webinars. One by myself and my colleague, and then another by my colleague Ruslan Bayguzov. This was, I think, 3 months. It was published 3 months ago. So go and find them. They're available on the internet. Okay. We also have Cloud Native Engine Service API, in which you can run simulation using a messaging service in the cloud, and this can be scaled up for running simulation tasks. Strongly. You can. We have also C++ API, in which it enables linking Pipesim with the third-party simulations, such as process simulators and so on. They're using this C++ API to link Pipesim with HYSYS, Pipesim with Honisim Honeywell. Honeywell product, forgot the process simulator name. So and this is an API that will work on the low level of the model. So as you can see here, we have various levels of openness, extensibility, and automation that help different levels of users to interact with the model without actually opening the Pipesim user interface. And finally, what are we developing this year? So this is under development right now. We're so excited about these functionalities. They're not finished yet, and we're not sure if this is going to be released in December. Maybe we'll push it sometime in Q1 next year. But these are really very strong and unique functionalities. So we are upgrading the will editor to include various advanced will configurations, such as dual strings. Such as dual strings, in which you have two tubings in the well. It could be two producer tubings, or one is producer, one is injector. We are also enabling concentric tubing, in which this can be used for cold tubing lifting, or for injecting two fluids into the well for SAGD operations, for example. We're enabling modeling what we call tailpipe, which is a tubing that can be installed at a certain depth to control production from certain areas. We're enabling also flow control valves to be independent from the completion, and exposing these into the user interface. We are enabling modeling this ESP separated gas hydraulics into the annulus. And this will, of course, can be used for steam circulation in SAGD operations and cold tube lifting. Symmetry enabled as a PVT engine from Pipesim compositional UI. This is going to be, for sure, part of 2022 release, which is going to be released in a few months this year. I believe that's it for presentation. I know people don't like slides so much. They are boring, and I agree with that. So let's go to the software then. As I said, guys, if you have any question, please type it in the chat, and then we can take them at the end of this presentation, okay, of this webinar. So I have opened Pipesim. So this is Pipesim 2021.1. This is the most recent official release. So this is what you see when you open Pipesim the first time. You see two tabs. One tab called Workspace, okay, and another tab called Home, okay. The Workspace will enable you finding the previous projects, or the previous models that you worked on, and you can create new or open existing network models or well models, okay. And then you will find the license information. If you don't have any license, then it's going to turn red, okay? Also, we have help here on the left. So you can click on the help, and then under the help, you see a lot of help material, including the case studies. So if I click on case studies, it will open a list of all the case studies that are installed with Pipesim. We have several well models. We have also several network models. We're going to touch them touch some of them, soon. We have also pipeline models, okay? And there is also training exercises. So these training exercises are used when you are when you register for an official Pipesim course through what we call Next program. So if you want to be involved in a certified official Schlumberger course, in which you will get a certificate from Schlumberger that you have attended this course, you just type in the net on Google Next Schlumberger training and put Pipesim, and it will take you to the page for the official Schlumberger training. And these are normally hands-on training. So, and of course, they are not free. Your company needs to pay for it. They are quite, not expensive, but for students, probably they're not affordable. These are meant mainly for professionals. And we have also tutorial examples. These tutorial examples are created for, based on the tutorials that are available in the help. So we have 8 tutorials, and if you go to the help, you'll find the step-by-step how to build these 8 tutorials. Like for example, let me just cancel and go back to the help. So if I go to workspace and then help, and then I open Pipesim help, okay? When you open Pipesim help, you will find, if I go to content, under content, you have 3 tabs, right? So if you go to content and then you go to tutorials at the end, expand this, you will find a number of step-by-step guide, okay, for several examples. And these tutorials, the end result of these tutorials are actually stored in Pipesim. Like for example, this case here, oil well performance analysis, all these step-by-step details to build the model. If you follow them, you will get the end result, which is the first tutorial. So if I go to Pipesim and I tell, let me just minimize this help. If I go to Pipesim and I go to case studies, I go to tutorial examples. The first one, you see this one is oil well performance analysis final. This is exactly the same as this tutorial here, oil well performance analysis. So if I open this tutorial here under this folder, okay, if I click on open, it will open the model that you should have created by by following these steps. Okay, so these steps will tell you actually how to do things, how to add equipment, how to run simulation, and how to get results. And I recommend that if you really want to learn Pipesim, and of course you'll need Pipesim to be installed in your machine, then you go and follow these instructions. And these are really comprehensive with a lot of explanations that can help you. And once you're done, you can compare your work with this tutorial, okay? With this model from, again, if I want to show you, you click on open, for example, or sorry, you can go to help. From help, you go to case studies. Under case studies, you go to tutorial examples, and then you open these exercises. So these exercises, as I said, these models are the final result that you should have achieved when you follow the instructions, that are available under the tutorial folder. Okay, these are quite good, comprehensive examples that, if you really master, then you can consider yourself, I would say, an intermediate user. I wouldn't say an expert, but an intermediate user of Pipesim. And it will teach you a lot of tricks and I would say how to do things using Pipesim software. Okay. So this is the help. So let me just go back to Pipesim. Again, if I am, in the, we have also options. So under options, you can open you can see the units. You can change the units from here. There are certain plugins that you can add to Pipesim. These plugins are already available in Pipesim folders. And you have advanced, okay, such as the engine path, the performance curve, and don't think you will need this. This is the maximum number of processors for simulation, the catalog version, and the GIS map. And you can configure your own GIS map if your company has its own GIS service. Okay, so this is under options. Now let's go back to new. Okay, and now let's look into the well canvas. Okay, what we're going to do right now is that I'm going to build a very simple will model, and then this will show you how we navigate the different tabs and options for a will model. And then we will come back later to look into in the deep dive for will modeling. But as a start, let's build a very simple will model, starting from basically scratch case. So I am under new here, and then I'm going to click on new will. Now, since I have opened the previous model, it is asking me, do you want to save the changes? I tell them no. And now we are starting now a will from scratch. Okay. So this is the will perspective. As I said before in my slides, we have two perspectives. We have the will perspective, and then we have the network perspective. Under the will perspective, you find that there are, three tabs here in the beginning. The first tab is the home. All right. Under home, you can perform, you will see the tasks, okay, that you can perform, simulation settings, and fluid manager. Okay. So as of now, we haven't added anything. So you will see that really building a model is straightforward. So under the home tab, you will find these tabs here: general, deviation survey, heat transfer, tubular, downhole equipment, artificial lift, completion, and surface equipment. Okay. So if I want to build a new model now, I can either go directly to the deviation survey, okay, and enter the deviation survey here. I can start with that, or I can jump directly to the tubular, for example, and then I can add casing and tubing, by pressing this plus sign. This is one way of adding equipment, the first equipment, which is casing and tubing, right? And the default right now is that it's going to be vertical, right? So once I add my tubular, it will be considered as vertical, and then I can change that later on. Or you can start with this. You can start by saying my survey type is 2D, and then you will need to enter MD, or measured depth, versus true vertical depth. Okay, MD versus TVD, and then you can take that from Excel and paste it here if you want. Okay, for the time being, let's just focus on vertical, so that we will assume that it's a vertical well, and then we're going to start adding the equipment. The heat transfer right now, there is also a default value. Like, for example, the heat transfer coefficient, we are going either to specify the heat transfer coefficient, and right now the average heat transfer coefficient is U, and the U value input is single. So meaning that for this well, the U value, or the heat transfer value, all right, or the average heat transfer value, will be the same from the reservoir to the surface. Okay, and that's why I don't need to, I can keep this for the time being, and I leave the default. That's why I said you can immediately go to the tubular and start adding details, or if you want, you can start with the deviation survey or the heat transfer. Okay. Now, what I'm going to do, I'm not going to add the casing and tubing by pressing the plus sign here. I'm going to do something else. I'm going to go to insert. And as you can see here under insert, you will find all the different equipments, right? We have casing, tubing, and then the rest of the equipment. So I can add casing and tubing by either clicking the plus buttons here, or I can directly drag and drop. So when I put the cursor on any of these equipment, it will give you description of the equipment. What is the casing? What is the tubing? What is the choke? And of course, all of them are, straightforward, but sometimes you need to know what are these equipment are used for, okay? So I will click on, I will press my left button in the mouse, and then I'm going to drag and drop a casing here. So automatically you will notice that I have added a casing, and the default is 10,000 feet. Okay. Of course, if you want to, and immediately you can see that it's using feet and inch. Okay. And if you recall, we said that in the advanced, you can change the units. And as a matter of fact, if you under home, you will see that you will find actually the units here where you can change from field to metric. If I put metric, automatically you'll find that it will change into meter and millimeter, and then also the pressures and so on are going to change into the metric units, or you can use the SI. Okay. And if you have a specific field units or specific units that you want to use, this where you can go to workspace, and then you go to options, and then under options you will find units here. Then you can actually add your own unit. So either you can import a unit system, or you can start with one default unit and then you click on clone. So for example, you have your own special version of field units. You can clone the field units, give it your own name. For example, I can call it my units. And now it will start with the field unit as the reference base model. And then you can change any of the units parameters. And then once you're done with that, you can, I click close, okay? Then you can simply find that my units now are added. Of course, I didn't change anything right now, so that means it's going to be it's going to use field units. I don't know about you, but I'm normally more comfortable in field units, and that's why this is what I'm going to use in my exercises. If you have your own version of the software, feel free to use your own unit, and feel comfortable with that. Okay, but for me, I'm going to use the field units. So as I said, when I added my first casing, okay, the default is 10,000 as the depth, and the inside diameter is 4.778 with wall thickness of 0.361. So there are two options here. You can either use the wall thickness or the outside diameter. So if you change the outside diameter, you will find that this is the outside diameter. You can select a specific casing by clicking on this button here. If you click on this button, you can actually access the pipe catalogs or the casing catalog that we have in Pipesim. You can search for specific inside diameter. Okay, like for example, you can, if you want to have it, if you have a specific inside diameter, you can type this. Like for example, I want, you know, a casing inside diameter of, for example, maybe 12. We just type, okay, we just maybe 7 inches. So I don't have a specific one. So what I can do is that I can say that, okay, less or greater than 7, and now it will list for you all the casings that are more than, because right now the default is equals to. Okay, so if I have a specific inside diameter, I can type that. Like for example, I tell him equals to 7.511, 7.511, and then it will list all these casings. Okay, or as I said, you can say that I want it to be greater than, let's say, 7, and then it will list for you all the casing inside diameters that are greater than 7. And this applies to everything here. Okay, we have the API catalog. We have other catalogs as well, right? So even from Tenaris. And we are also adding and updating these catalogs frequently. Hopefully, we are going to also have another catalog soon. So it will be added to the system. Okay. Great. So now, again, we are here in the casing. Okay. Now, when can I check if I am, because I'm getting warning that, let me see here. My computer needs an update, so let me know if we're having any issue in the connectivity. Okay, so and if we're okay, I think we can continue. Just a second, please. Okay, are we all good? Perfect. So let me also, because I'm seeing that. Okay. So we are here. Now, what did I do so far? I have added a casing, right? With the inside diameter of 4.771. And then, as I said, I can select a different casing from this catalog. Okay. And I can change the depth manually. Like, for example, I can type 9,000 here. And then I can add another casing. So what we can do is we can add number of casings that are, that represent my well. So, for example, we have, let's say, 3 casings. So the first one actually is going to be with the inside diameter of, let's say, 12 inches. And let me use wall thickness. So wall thickness is let's say 3. Okay. And this goes all the way up to, let's say, 500. Okay. And then we have a casing that is probably 10.125. That goes up to, let's say, 3,000. And then we have a casing that is 9.5 side diameter, and it's going, or maybe 9. Let's say 2, and it's going up to, let's say 7,000. So as you can see here, we have these 3 casings. Okay, and I can now add my tubings. As I said before, I can click on the insert and go to the tubing, and then I can drag and drop a tubing here. Okay. Now, the default tubing right now is going up to 3,500. So I can change that to be, for example, 6,700. And now, as of now, I'm done with my tubular. Okay. So I can now continue to the, and now, as I said, I'm going to leave it as vertical. I'm going to leave the heat transfer, and then I'm going to start adding downhole equipment. So right now, as you can see here, the inside diameter of the tubing, let's say we are using 4.5 tubing as inside diameter. Okay. And now, if I want to really model the flow direction, I will need to put a packer, right? The packer is considered as a downhole equipment. So if I click on plus, and I can also add a packer by drag and drop, but let me just do that now by clicking on the plus sign. And then I'm going to say that I have a packer that is at 6,650. So this is my packer. Okay. And now I have identified my flow path. So I'm going to add a completion now here at the bottom of the casing, and then the flow will go in, will be forced to go inside the tubing only. Okay. So artificial lift, I'm not going to add any artificial lift right now. So that's why I didn't add anything. I'm going now to add a completion. Similarly, as similar to all the equipments and objects inside Pipesim, I can drag and drop, or I can add, a completion here. Okay. Let's drag and drop now. So if I'm going to press the lift button, and then I'm going to place this completion here. Now the completion has been added. And as you can see here, it is now starting to complain about missing data, right? So if I click on this completion, now I can see that I have this missing data that are not added yet, or I can directly go from here, and then I can go to any of these. Let's say if I am in the general, I don't know what's my missing parameter, why it's complaining. So I can just hover over this validation section, and then I can click on any of these links, and it will take me directly to the missing values. So now let's talk about the completions, how we can model completions. So in completions, we have several options. We have geometry profile that is vertical or horizontal, and the entry point is either single point, or if I have horizontal, then it could be single point or distributed. Again, under geometry profile, if I say vertical, there's only one option for the fluid entry, which is single point entry. For this single point entry, I have a list of IPR models. IPR stands for inflow performance relationship, and this is how we describe our reservoir or our completion, or how what's the relationship between the flow rate and the drawdown in the reservoir. So there are different IPR models that are associated with vertical geometry and single point fluid entry. Some of them can be used for oil, for liquid and gas. Some of them are only available for gas. Like, for example, if I say well productivity index or well PI, I can base it. I can use the liquid basis PI or the gas basis PI. Let's focus on liquid basis IPR for the productivity index, and let's start entering some numbers. So reservoir pressure. Reservoir pressure, let's say that our reservoir pressure is 3,200 PSI. Forgive my voice because I have a little bit of cold, but unfortunately, it happened just a few days ago, so I apologize for that. Reservoir temperature, let's say our reservoir temperature is 190 Fahrenheit, and the productivity index is, say, 5. Okay. Now, it is still complaining. Validation. What is missing? It says no associated fluid. So I directly go to the fluid model, and as you can see here, it says that no global fluids available. Or if I am here and I again click on this link, it will take me to this section here. So I need to add a fluid to the well. Specifically about fluids later on, because we have different fluid options in Pipesim, but the default when you open a new model is black oil. The difference between black oil and compositional or PVT file or multi-flash file, I'll describe this later, but in simple terms, black oil uses correlations as is described here. It says that correlations are used to calculate the vapor and liquid fractions, thermodynamics, and transport properties. A key benefit for black oil model is that they may be readily used, available, readily constructed using available field data. Anyways, so the default is black oil. Okay. If I click on black oil, you will see that I need to add a fluid to the system, and I can do that immediately by clicking here, this new button here. So when I click on new button, right, it's asking me, do you want to start with a template? Like, for example, we have a few templates here for dry gas, light oil and gas, heavy oil and gas, dead oil or water. I'll tell them, yes, I'm going to start with light oil and gas. And then when I click on OK, it creates for me a basic fluid that I can name it. Let's say my fluid. Okay. And then it has some basic data that I can immediately change. Like, for example, the gas oil ratio, let's say my gas oil ratio is 350 standard cubic feet per stock tank barrel. The oil API is maybe, let's say, 32. Gas specific gravity is 0.85. And I will leave the water specific gravity as 1.02. And then I'm not going to add any fractions, okay, any contaminations such as CO2, H2S, nitrogen. And I'm going to leave everything else as default, like viscosity. There are different correlations for the viscosity. Also for the emulsions. Calibration, I'm not going to add any calibration data. And I'm going to leave the thermal values as is. So as you can see here, the only thing that I have changed is that I have changed the fluid name. I have not entered any water cut. I said that the GOR is 350, changed the gas viscosity, left the water specific gravity as is, and changed the oil API. When I click on close, then the completion now has been associated with my fluid. When I click on the reservoir fluid, you will see that automatically the system has created my IPR curve. And all the validations are gone now. So with this, I have constructed my first well model. I will say again what we have done. So under general, we didn't change anything. Under general, you can find the well name and then whether the well is production or injection. So the well is production right now. Check valve settings, block reverse. So this is used when you add the well to the network. I did not change the deviation survey, so the well will be considered vertical. I did not change the heat transfer. We're using heat transfer of U of 2 for all the well completion. So depending on the heat transfer of the geothermal gradient, the temperature of the fluid will be exchanged using this value. And as you can see here, we have soil temperature at wellhead, which is 60, and then we also define the reservoir temperature. So we have now 190 here, and then we have 60 here. So this creates a linear profile for our surrounding, right? And then we're putting U as of 2 U value. Then this is how the fluid will exchange its fluid with its temperature with the surrounding, or the heat with the surrounding, so that its temperature will change. I did not add any downhole equipment except the packer. I did not add any artificial lift equipment, and I just added one vertical completion at this depth. I use well PI as my IPR model. I entered the reservoir pressure, temperature, productivity index, and then the fluid model is my fluid. And this is my fluid. Okay. With that, I'm ready to perform my first run. Okay, so in order for you to know how much the well should produce under these conditions, you have several tasks. One of them, of course, is the famous one, which is nodal analysis. So what is nodal analysis? Nodal analysis is a simulation task that when you run, it will create a node in the system. Right now, the node location is at the bottom hole. When I click OK, you will see that there is a new symbol here, these lines, that indicates the nodal analysis point. If you want to understand more about nodal analysis, I have also posted a previous Pipesim webinar in which I talked specifically about nodal analysis. I think it was actually a webinar on nodal analysis. It wasn't really about Pipesim, where I described in theory how nodal analysis works and how the system would construct the inflow and the outflow curves. Okay. So the first thing when I see when I launch my nodal analysis task is that I have a new validation, and the validation is clear here. It is asking me about my outlet pressure. So what is the outlet pressure? And in this case, I did not add any surface equipment. So that's why my outlet pressure is at the wellhead immediately. That's why it says the branch end at the wellhead. So when I say that my wellhead pressure is 300 psi, the validation is gone, and now I can run my nodal analysis task. This is the reservoir pressure. This is the outlet pressure. When I click on run, this is my nodal analysis curve. And now the simulator or the Pipesim is telling you that this well should produce 5,974 barrels per day. A healthy well, strong well. And as you can see here, this is the inflow curve. This is the outflow curve. Okay. This is the IPR, what we call it, and this is the VLP. Okay. Now, one of the things that I'd like also to see is the bubble point location, so that I can avoid producing below the bubble point, and I can also view operating envelope. The operating envelope is basically this box here. What is this? So number one, on the left-hand side, this is what you call the inversion point, meaning if you notice that this outflow curve, it starts going down, okay, from the reservoir, from the wellhead plus the hydrostatic pressure point. And then as the production increases, the bottom pressure will go down. This is what we call the unstable region. You don't want the intersection between the inflow and the outflow to happen in this region. And then from this point onwards, the outflow curve becomes either horizontal or going up. So this is your inversion point. So you would like to always produce, or you'd like to always make the intersection between inflow and outflow beyond this point, which is what's happening here. The other line, or the other red line here for the other limit, is the erosional velocity ratio maximum. So if your intersection is happening at any point beyond this line, that means your well is going under erosional issues. For this line here, this is the drawdown limit. The drawdown limit is defined based on this value. So how much you would like to produce with respect to absolute open flow. The absolute open flow is the maximum theoretical production that you can produce from the well. And the top one here is the reservoir pressure, of course. You cannot produce more than this pressure. So this envelope here is very useful. If your intersection is within this operating envelope, then you're good. Okay. So I'm going to close now or before I click close, let us see what other information do we have. So we have the system results. We have the profile results. So what is the profile results? The profile results is basically you want to see at the operating point, this one here, at this rate, what are your operating conditions? Like, for example, you can show the elevation versus pressure. So this is the pressure distribution. And as you can see here, this is the reservoir pressure, 3,200. This drop in the pressure is what? This is the drawdown in the completion. Okay? And you will see that, for example, the flow bottom hole pressure is around 2,000. How can I see that? Well, if you go to the system results and you see the intersection or the P at the nodal analysis, it is 2,500. So this is the flowing bottom hole pressure at this point here. Okay? And this is obvious from this curve. And then from this point upwards, this is the pressure profile of the fluid until it reaches, of course, 300, which is our outlet pressure that we defined in our system. Okay? So this is the profile result. And then you can plot anything else. You can also add another plot, another curve on the same plot. Like, for example, you'd like also to show the elevation and in addition to on the right y-axis, you would like also to see the temperature, for example. So now, as you can see here, this is the temperature versus elevation. Okay. Or you can see something else, such as, let's say, for example, flowing, or let's say liquid velocity, for example. Okay, so this is the liquid velocity, and there are many other plots. If you want to see numbers, you can go to show grids, and then you can see everything. So all these details are available. You can select whatever you want to see. Okay. At the operating condition. So this is the operating condition, okay? So this is the nodal analysis. Now, before leaving the nodal analysis, we have what we call the sensitivity analysis. So you can perform sensitivity by simply going to, if it's inflow sensitivity, then you select completion. This is the completion name. And then you'd like to change the reservoir pressure, and then you can, because we have the reservoir pressure of 3,500, let's see the impact of changing the reservoir pressure on the production. So what if our reservoir pressure goes to, let's say, 2,000, and then the maximum is 3,200, of course, and then the step is maybe 300 psi. I'm now creating 5 steps starting from 2,000 until 3,200. And let me run all these nodal analysis cases. As you can see here, this is an excellent plot because it tells you now how your system will perform under different reservoir pressures. For the reservoir pressure of 2,000, there is no intersection between the inflow and the outflow. And this shows that the well cannot produce under these conditions if the reservoir pressure drops at 2,000. And it's also interesting because it appears to me that the last possible reservoir pressure where the well can flow is at 2,300. You see here, this is 2,300. And this is, it's barely touching. So that's obviously our last possible operating point. However, you will notice that the intersection here is happening on the left-hand side of the VLP curve or the outflow curve, which is, of course, not preferable because the production will be considered unstable. Similarly, it seems that this also reservoir pressure, because also this is still on the left-hand side. The well did not start going up until I think these 2 points. Okay, so this is an interesting curve, and we can also add any other sensitivities to and plot them into the nodal analysis, and each of these points, operating points, I will have the profile result that I can actually plot, everything I want, or anything I want from this list. Okay. I think now we passed 1 hour 15 minutes. I think we are due for a break. Okay. So now let's have a break for 15 minutes. What I'm going to do right now, I'm going to put a counter on my screen. And then for 15 minutes, and then we will see each other after 15 minutes. Okay. So let's say time counter. Countdown. Let's see. No, not this one. What is this? Stopwatch. Okay. Agree. Timer. Let's put 15 minutes. 14 minutes. Okay, and then we will start. Okay, we will meet, guys, once this timer is finished. I'm going to stop my video, and then we'll see you later. Okay. Hello, everyone. Let's get started. Let's continue. I hope that I'm loud and clear. So what we have done so far is that we have, went through the different tabs of the well canvas. We looked into how we build a well model, a simple well model. We will come back to the well later on for more deep dive. But now let's have a look into the network canvas. Okay. Now, from this home tab, as you can see here, I can directly switch to the network canvas. Okay. So when I click on network here, the same well now will be taken to the network. Okay. And under network, when you click on the insert button, you will see that the objects that we can add to the system has changed, because previously we used to have things related to the well, such as completion, tubing, casing, and so on. Okay. Now we have the objects that will enable us to build a network. Okay. Now on the left hand side we have source. This source, basically, you can it's a boundary condition that you can specify. If I use, for example, the same fluid, I can specify the surface temperature and the surface pressure downhole of the choke, and this will represent the inlet to my system. Like, for example, this could be my wellhead, right? Without the need to include all the well details. And this is the well that we worked on before the break. And then if I simply double click on this well, you will see that all the data that I have constructed are there. Okay. And I can look into the well details while I am still on the network canvas. So I don't really need to switch to the well canvas. I can, simply double click on the well, and then I can look into the data. Okay. So this is a source. This is a sink. Okay. The sink can only be a pressure sink. Like, for example, I can specify the pressure to be, for example, 150. I can have a junction. This junction is basically a gathering point. So if I connect a connector from the source to the junction, that means those two are the same. There is no difference in terms of, there is no pressure drop. But if I add a flow line between the source and this junction, then this flow line, I have to enter the details of this flow line. When I double click on this flow line here, I need to enter the inside diameter. Let's say the inside diameter is 4 inches. And the length of the horizontal distance is maybe 150 feet. And there is no elevation difference. As you can see here, Pipesim by default creates or adds a value of rate of undulations. So undulations is a value that you normally add to cover for let's say small changes in the elevations. And as you can see here, what it says that the rate of undulation is 10 for every 1,000. Okay, so which means that in visual sense, it just says that, okay, for the 150 along the 150, this is how much is expected in terms of elevation change. Of course, if you don't want anything, you can just say 0 here, and then the pipeline will be flat. Okay, so this is the flow line. The flow line can be defined as either pipe or annulus if you have a pipe inside a pipe, or you can change the mode for this flow line by going from simple to detailed. If you go to detailed, that means you will need to enter more, you can enter more details to the pipeline. Like, for example, the general data now changed to in simple. When I was under simple, I just entered the horizontal distance and the elevation difference. That's it. Okay. Okay. What if you have changes up and down? Then you can simply go to detail, and then you can either enter the distance as horizontal distance or measured distance. So if you enter the horizontal, that means this is the horizontal distance, and then at each of these points of the horizontal distance, you can specify the elevation. Like, for example, let's assume that at the middle of this pipeline, the elevation is changing to, say, for example, 20 feet above the ground, and then it will go down. So it will become something like this. And of course, you can have a full detailed many more points if you want to, and you can specify the elevation difference for this flow line. For the heat transfer, it can also open up a complete, I would say, detailed calculation for the heat transfer calculation. You can either specify one value, okay, or you can click on calculate, and then when you click on calculate, you can actually go and enter several pipe coating details, pipe coating layers, and each of these pipe coating layers can have a different thickness with thermal conductivity, and then Pipesim will calculate the heat transfer, the overall heat transfer for you. You can also say whether you are connected to the if your pipeline is buried, for example, or not. Like, for example, I can say that my pipeline is, let's say, in feet, for example. So let's say it's half a feet or 1 feet burial depth. Then automatically the pipeline will be buried, and then all that will be taken into consideration while calculating the heat transfer. Okay, so going back to simple now. Again, we are going to this pipeline here. Okay, so it's a horizontal distance. It's nothing but the horizontal distance 150, inside diameter is 4, and that's it. So now I can simply right-click copy, and then right-click paste this pipeline, and then I can connect now like this, drag and drop. So what did I do now? I have now connected my flow line to the source and to the well, and then I'm going to add another flow line from this junction. So as you can see here, the way I do it is that I click on the flow line, and then I move my cursor until I get closer to the junction, and then automatically it will realize that I'm close enough. When I click now and I hold my button, I can drag and drop the other end, and now I have another flow line that I have added now. Double click, okay, and I can say that the inside diameter is now 6, and let's say the horizontal distance is 1000, and there is, let's say, no rate of undulation if I want, okay, and that's it. I will leave everything else. Now I have built my network. So I have a well, right? I have a source. From this source, I have a flow line that is 150. The same flow line is also copied here from this well to the junction. And then we have this flow line, which is 1000 feet, okay, distance. Now that's it. My network is ready. I can start running my network. So if I go to the home button now, I can click on network simulation, and now I can run my network simulation. However, before I doing so, I need to know what correlations am I using, okay? So if I go to, or what flow model I'm using. So if I go to simulation settings, you will find now that I have several options here. For flow correlations, I can select my vertical and horizontal flow models. It's always recommended that you use Olga-S. So the source is Olga-S. And now I can use the Olga 2017 3-phase or 2-phase. That's the main difference is in the viscosity calculation. For the horizontal flow, we can also go to Olga-S and 3-phase. And of course, you can select whatever you want if you wish. You can go to, for example, Baker Jardine. Baker Jardine was actually the initial owner or the initial developer of the Pipesim, which then was acquired by Schlumberger. As you can see, if I go to Baker Jardine, you will find all the original correlations: Biggs and Brell, Mukherjee and Brell, and so on. Okay, and but I'm going, as I said, and I'm going to use Olga-S 3-phase, no HD, so just 3-phase. And now these are the correlations that I'm going to use. And if you want to use a specific correlation for a specific flow line, you can simply use local, and then you can override. You can basically specify for each of the, whether it's a well or a flow line, you can specify certain correlation for that piece, okay, for that flow line. Like, for example, if I tell them I want to use for this flow line FL a special correlation, I can simply override, and then I can define whatever correlation I want for that particular. Otherwise, I'm going to use so if I go to use global, that means these correlations are going to use for all the wells and the pipelines, whether it's either it's horizontal or vertical. Heat transfer, the pipe burial method. So we have three methods: 1983, 2000 method, and 2009 method. These are Schlumberger methods, and the inside fill coefficient is either Kaminsky or Keith, and the U-value multiplier if you want, and also you can use local. Erosion, corrosion. So I unfortunately don't have time to go into these details, but I just want to show that under corrosion you can select TPA, corrosion model, from Trusted Pipeline Advisor. This TPA requires a special license, and it's really useful. You can also look into my. We have also a published webinar that I've done on Trusted Pipeline Advisor. If you're interested, along with the author or the owner of the Trusted Pipeline Advisor, David Richardson, you can look into that onto the internet, and so on. Advanced, I will not go through it. So right now I'm ready. So I just wanted to show you that this is where you change the flow correlation. And now if you click on the network simulation, then it basically brought the boundary conditions. So as you can see here, these are the boundary conditions that we have. So for the well, we have the completion, 3,200. We have one source. This is the pressure, and one sink, which is 150. And when I click on run, basically the whole system will be calculated. And now, as you can see here, the well, we have what we call node and branch results, and we have profile results. So starting with node and branch results, we have node and we have branch. So nodes are basically point objects. Like, for example, we have here a well. This is the result is shown as a node, and as you can see here, it says that this is the pressure at the outlet of that branch. Okay. And this is the completion. So if you click on this plus sign, you will expand the completion details. And then you can look into that completion that is part of the branch well, right? We have, this is the static pressure, this is the flow bottom pressure, this is the drawdown, and this is how much the well is producing. So the well is producing liquid rate of 6,166. And these are the node results, okay? Point results. If I want to show delta results, that then I can go to the branch option, and then you can see for each of the branches. So this is a branch, So the branch is called, if it's an inlet branch, the name will be called by the inlet point. Like for example, I have a branch called well here. I have another branch called source, and then I have another branch called sink. And if I have an intermediate branch, then it will be called by the two intermediate points. I can show you in the middle. But as you can see here, each of these branches, we have delta P. So delta P, delta T, the liquid rate, oil rate, and so on. And if you want to see more values, you can click on columns, and then you can select whatever you want to see for that branch. And then we have the profile results. The profile results is a result for each branch. Okay, so if I click on source, these are the profile results for that branch. I can also select all of them by simply clicking on the shift button and then clicking here. It will select everything. And now when it selects everything, it shows you all the details for all the branches. And click on show plot, and then you will see now that this is the green one is the well branch. This is the reservoir pressure. This is the bottom pressure. This is the pressure. And because on the x-axis is the total distance. And as you can see here, these this blue dots here is basically what? Is the source, right? So now this will be clearer when we have more wells and branches, but I'll show you this in a moment. Just focus. If I uncheck the well, you will see what I'm talking about. So we have this branch here is for the what? For the source branch. This is the sink branch. And then if I check now the well, you will see the whole range of the pressure. Okay. So this is a small network, okay, that I have just built. And what I'm going to do right now is that I'm going to show you several examples, okay, of networks that will indicate and will show different functionalities in the software. So what I'm going to do right now, I'm going to go to workspace, and then I'm going to help case studies, and let's have a look into several networks and several wells, okay, to have an idea about more functionalities. Now let's have a network with a GIS system or a geographic information system. So if I go to under case studies, network models, I can find a number of network models. Some of them are GIS. So for example, I have this network here that says gas gathering network GIS. When I click on that and I click open, or I just simply double click. Now, do you want to save? No. So this is an interesting network, okay? You will see that now if I zoom in, I find that there are numbers here and there are clusters. These clusters, just to show you that, okay, for these clusters, you have two objects. These are two objects, and I can hide these clusters by going to format and then uncheck cluster. Why do we have clusters? Let me show you why. When I uncheck this cluster, you will see that if I scroll down, okay, the compressor and the heat exchanger, okay, are actually connected by a connector, okay? So in reality, where is because when say there's a connector, that means there is no physical distance between the two. And that's why we enabled the clusters, because once you click on the cluster, it will show you the actual flow line path and where are the two equipment belong. Because the moment you say you uncheck the cluster, okay, then you can add this flow line here, and then you can place different objects that are on the same location, right? But you can put them far away a little bit, okay? So now let's zoom out a little bit. So what do we have here? So in order to move my GIS map, I need to hold the control button and then I press the left button in the mouse. Now let's zoom into this well. Okay, so we have this well, and then we have this well going this flow line, right? So let's have a look. So double click on this well. Then we have this information of this well. Okay, it's a producer. This is the deviation survey. It's a vertical well. This is the heat transfer coefficient. Tubular, we have one casing and one tubing as indicated here. Go to the completion. Let's have a look into the completion. So we have a gas IPR using Darcy model. So this is the reservoir pressure. This is the details, for Darcy. And then this is there's a skin value of 1.5. And this is the fluid model that we're using. If I want to see what fluid I'm seeing here, I can click on edit. And then it will show me that this is the fluid associated with this well. The fluid name is gamma. The GOR is very high. So obviously this is a gas well. Okay. And now, if I want to see better, let's say, unit, I can simply change the GOR to become OGR, or condensate gas ratio. Okay, but it won't be automatic, but I can use that unit differently. So now we have now 596 gas standard cubic gas per 596,101 standard cubic feet per stock tank barrel of GOR. Okay, so this is obviously a gas well, and this is the IPR automatically created for this well. Now let's have a look into this GIS information. So this 5 branch here connecting this well to this junction, if I double click on it, you will see that it has this deviation survey. And this deviation survey was actually populated from the GIS automatically. Now, what we can do here, as you can see here, we have the pipeline is 2,300 feet long, but then we have few points, right? What if I want to add more refinement to my pipeline and populate more data from the GIS? Okay, as you can see here, and that's as indicated here, the flow line is going down in the beginning, right? And then it starts going up. Okay, so if I go now using the same data source, which is Esri, what if I tell him I want the interval not to be 300 feet? I want the interval to be 100 feet. And I click enter. As you can see here, I have lost my original deviation survey. So I need now to call the GIS service and I tell them, create the elevation for me again. I hit the capture button, the capture elevation button here. When I do that, you know what will happen? Pipesim will send these latitude and longitude that are created on these pipelines, because now automatically Pipesim has created what we call GIS nodes. Okay, and automatically it's going to capture the elevation and the length using these latitude and longitude, which is coming from the GIS mapping service. So when I click on capture elevation, look what happens now. Now we have better profile. Okay, and this is done for all the pipelines. Let me just remove the GIS nodes. So this pipeline, for example, here, we have now better representation. See how powerful this is, because this is very, very useful. Now, for all your network, you don't have to go into each flow line to enter the pipeline profile details. It is automatically captured from the GIS system. Let me do this again for this pipeline, for example. Here we have, you know, initially we have the 14 points, because you see, I put that the maximum points is 50, okay? So if I say the maximum points is more than 50, then let's say the maximum points is 100, click enter, and then click capture elevation again. See now, it managed to capture, you know, much more points. And I have now better representation of my flow line, okay? Of course, the more flow line details you add, you expect that the performance will be slower, sorry. That's why you will have to make a decision of the optimum number of, you know, deviation points, okay? Like, for example, if you say that maximum points is 50, okay, then you basically capture the elevation again. Then now you know that, okay, you have 50 is the maximum number of the nodes, and then you have additional GIS nodes. What are the GIS nodes? The GIS nodes are the ones we use when we constructed this flow line. Because while I construct the flow line, I'm going to click on the GIS. So now we have the GIS, you know, point. So this is the GIS node, right? And also we can show, just a second. Can show the, what is it? The elevation points. Yeah, we can also show the elevation points. Now, as you can see here, these elevation points are, you know, created based on these numbers, and it will add to that these GIS nodes. So that's why when I put 50, not necessarily it's going to be 50, because I'm going to have 50 elevation points in addition to the GIS nodes for each of the flow lines, okay? So let's now remove the cluster, and then we have now, you know, the cluster points are already, you know, removed, and this is now our flow lines. And as you can see here, as I said, this is very useful for you. Now, suppose I want to drill a new well here, okay? How am I going to add a new flow line to my system, okay? So let's say I have a well that's going to be drilled here. So what I'm going to do right now, I'm going to insert a well. Or in the beginning, let's assume that I'm going to insert a source. I don't want to enter the well details right now. The well has not been drilled yet. But what we are going to do, this is where we have identified the well location. We are expecting that the fluid is going to be taken from any of these reservoirs. And this is the expected, let's say, surface temperature of the fluid. And the pressure, let's assume, is going to be. So now I have defined what? I have defined my wellhead locations or wellhead conditions. And now I want to add a flow line. Let's assume that I'm going to follow this path here to add my flow line. So I'm going to click on the flow line. And while I'm here, you know, as you can see here, when I get close to the well, it found a node, and then I'm going to click, and then I'm going to start digitizing my flow line by clicking on the map. While I click on the map, it's going to add a GIS node. See, now I need to move down, so I need to click Control. Let me just click Control like this and press the button. Now I have reached here. Now what do? I need to add the well to this point here, okay? So now the only thing I can do that is by simply, splitting the flow line at this point. So I go to split flow line, and then I'm gonna click here, and now my flow line has been split. And now I'm going to simply connect this point here, and now I have added my flow line. And now I simply need to recapture the elevation. So click on Format, Capture the Elevation. And now the elevation has been captured for this flow line. However, I did not enter the inside diameter. So it found the length automatically. It found the elevation profile automatically. The only thing I need to do to add is the inside diameter, and that's it. You see, our flow line has been added. And now let's run our network simulation now. Okay. So when I go to Home, I click on Network Simulation. Now it tells me that you have missing boundary condition. Why is that? Because as you know, I have added a new source. So I'm gonna find this new source. Okay, so this is the source. And then I'm gonna say that, okay, for this source, the pressure, if I click on reset boundary conditions, I think it will get the pressure. Yes. So when I click on reset boundary conditions, it found the pressure in the source, and then it added it here. And now I can simply go and click Run. So now my network now is being solved using all the pipeline profiles that I have entered, and starting from the wells, from the well boundary conditions at the reservoir. The network has converged now, and these are my results. Now, let's look into the results in a different way. So let me just close this guy here. And now, let's look into the annotations on the map. Now, these annotations are what? These are pressures. But then, if I want to have more data, you can simply click on this drop down, and then you can select whatever you want to see. Like, for example, here we have selected the internal node pressure, the sink pressure, the sink gas rate. But I want also to add the wellhead gas rate. Okay, so I'm going to go to wellhead gas rate. And then I'm going also to add the source gas rate. So you see now, for this source, I defined only the pressure, and it told me for this pressure, you can inject 27 million standard cubic feet per day. And this is how much each well is producing in terms of Q gas. What if I want also to add, to visualize the pressure at the wellhead? You can do that, of course. You can go to annotation, and then you can go to wellhead pressure. Now we have the wellhead pressure. We can also show the wellhead temperature. Literally, I mean, all these values can be shown here. So this is the annotations, okay? This is one way of displaying results. Suppose that you feel that, well, my network is becoming busy, okay? I need a better visual representation. Well, you can always switch to the network schematic. When you go to the network schematic, you don't now have to stick to the GIS. So you can actually look into the, the network in a different canvas by change. And if you change the location of any of these objects, it will not affect your GIS. Okay. So this is another way. A best way, of course, is to hide the annotation and then go to Format, and then show the results gradient. So now this is the results gradient, okay? And as you can see here, the results gradient, this is the the distribution of the values, okay? And you can go to the, for example, this, I'm showing the pressure gradient. I can show the temperature gradient. I can show, for example, the corrosion rate. So this is very useful, huh? As you can see here, this pipeline here has high corrosion rate. So then you can focus on this flow line and prepare for handling for pipeline integrity measures for this particular flow line, right? Similarly, this flow line. So as you can see here, this color-coded result gradient is very useful for you to identify issues quickly and try to focus on certain objects or certain maybe flow lines or wells to prepare for any remedial action. Okay, so now we mentioned how we show wells, how we build wells, and how we show the results in the network. So we still have now less than an hour. Actually, we have about 40 minutes because we will need to have 15 minutes for Q&A. So let's now have a look into the different well options, the well capabilities. So what I'm going to do right now, I'm going to go to the workspace, and then I'm going to help case studies. And let's have a look into the different options. So for example, if I go to this first example, basic oil well. This is an oil well with one gas lift valve. So if I open this well, now what do we have here? So as you can see here, this is a well, one tubing, one casing, one completion, but then it has one gas lift valve. So modeling gas lift in Pipesim is very powerful. Okay, and we can model gas lift using different levels of details or different levels of complexity. Right. The easiest is to define the gas lift injection rate at any depth, and for that, and this is all of what you need to care about. For example, if you want, you can simply click on or use fixed injection ports. When you click on fixed injection ports, basically you can define the injection gas rate. Like for example, you say that I want to inject, for example, 2 million standard cubic feet per day at this depth. And that's it. You don't want to calculate any additional calculation, right? And for that, you can simply click on the PT profile. Yeah, one of the things I didn't show you is the PT profile, but I will show you that in a moment. You can go to nodal analysis and run the well. Let me just remove all the sensitivities. You can run this well, and you will see that this well is producing 500 barrels per day for this gas injection rate. Okay, you go to profile results, and then you see that, okay, go to show grid, and then you'll have, this is the completion, this is the depth, so the elevation minus 9,000, so this is the location of the completion, and then this is the completion, this is how much is the details, let's say bottom pressure, bottom temperature, and then this is the casing. We're going up, we have entered the fluid at the tubing, and then we found the gas lift port that is injecting this amount. That's it. The amount is 2 million standard cubic feet per day, and I did not ask the software to calculate anything further. This is the simplest way. Of course, I can do more, right? Using fixed injection ports, I can use a correlation to calculate the stability of this gas lift valve by enabling AHMAD stability check. So if I enable the AHMAD stability check, so this is the first level of complexity, or the first level of not complexity but details that I'd like to add. The more details you would like to calculate, the more data you need to enter. Like for example, when I check this one, now you need to enter what is the port size. So I would say that, okay, the port size now is 0.125 inches. Then I need to enter now the surface injection pressure and the surface injection temperature. So let's say the surface injection pressure is 1,500 psi. The surface injection temperature is maybe 60. And now when I click on the same task again, the same nodal analysis task again, now remember that we produced 500, right? Now, and if I click run, I also produce 500. And there's there's no difference in the details. But when we added this information, the port size, the injection pressure, and the temperature, we will be able to see more results. When I go to the profile results, and then I go to the show grid, I go to the gas lift port. Now I can see that I have the flow rate, I have the casing head temperature, IP temperature, delta P. So this is the pressure drop across the the gas lift valve, and now this is the Joule-Thomson effect across this valve. Okay. Now, if I also want to see more details, I can go now to the columns. Okay, and now I can look into more details related to my production, the hold up, the velocity, and so on. Okay, and that's it for the gas lift fixed injection port. Now, if I want also to do more, let's even design a gas lift system for our well. So what we can do now is that we are going to remove this gas lift port. Delete. And now let's run the system without the gas lift. See how much we are producing. So if we go to nodal analysis now, and then we run the well without any gas lift, without any lift, we will see that we are producing 200 barrels per day. I want to increase that. I want to make it something like let's say maybe 400. Okay, I want to produce 400. How do I do that? I need to add gas lift. So now let's design a gas lift system. And now I'm going to show you how easy and straightforward you can design a full gas lift system to the well. So what you can do is that you can go to the gas lift design task, and I will tell them I want to produce outlet pressure at outlet pressure of 300, and the target injection rate, as we said, how much it was, 400 barrels, right? So now, no, sorry, this is target injection rate. So target injection rate 2. I want to inject 2, okay? And I now would like to see how the gas lift design task will help me distribute the injection gas, injection gas valves, the gas lift valves to inject 2 million standard cubic feet per day. Okay, so now when I click on run, the system automatically found that you will be able to inject, to install these valves here at these depths. Okay, and now if I go to the output summary, show grid, you will see that the design is telling you that you can install these at the valves at these depths, okay? And this is how much you are going to inject, okay? And then when you do that, your liquid rate will be 516, okay? What do we have here? I don't know. Anyways, so now when we inject 2, we are producing 500, okay? So now, hold just a second. Okay, I hope everything is okay. I just see that we have, what do we have here? It's fine, I hope. Okay. So now, and I said, you know what? Maybe if I want to produce less, let's reduce, then we don't need to inject that much. So I go now to the gas lift design, and then I tell them, what if I inject 1.5? How much I'm going to produce, okay? So I'm going to say 1.5, okay? And I don't want really to go into the details of the gas lift design because this is not the objective of this workshop today. But I'm going to say now for 1500, okay? And if I inject 1.5, how much I'm going to get? Now there's a new design, and now it's telling me if I go to the show grid, I'm going to produce, you know, 496. I have some warning here. The selected valve is at depth, blah blah blah. Support the gas injection. Okay, this exceeds the user special upper limit of 1.5. Fine. So now I can, if I'm happy with that, I can use it. I can go ahead. All right, or I can basically change the design settings. I can select different manufacturer, different minimum port size, and so on, and I redo my design. Now, if I go again to the design results, I will say that, okay, if you install these valves, then you will get this amount, okay? So now if I'm happy with this, I'm going to get to say, go to the design result, and I tell them install design. And now you will see that your system now has installed all these valves. Okay. And now we have automatically selected injection valve system. And this is the, you know, the injection gas rate, the surface injection pressure, and so on. Now I need to make even further calculation, and I need to make the calculation more sophisticated. So I want to tell him, you know what, enable multi-pointing, okay, and tell me when I perform this analysis now, I'm going to make some diagnostics, okay, meaning I'm going to see whether all the valves will be open or closed. Do you have multi-pointing or not under these conditions? But the diagnostics type is fixed injection pressure. So I'm going to honor the pressure, and I'm going to see how much we are going to inject, and which of the valves is going to be open, which of the valves is going to be closed. Okay? Because if I do not enable multi-pointing, the system will just inject it at the deepest injection valve. Okay? It will just consider that the shallower valves are going to be used for unloading only, and they're not operational. So based on this pressure, based on this rate, it will try to find the deepest injection point, and then it will inject this amount. But when I do enable multi-pointing, this is a more advanced calculation. It will honor only the pressure, and then it will try to achieve this rate, but then it will tell you whether you have multi-pointing or not. And now let's start looking into the PT profile. So the main difference between nodal analysis and the PT profile is that the PT profile, remember when we did the nodal analysis, we have the profile results, which is taken at this point here. So this is exactly what we are going to do in PT profile. So it's a quicker calculation. So now we're going to tell him run. And now the production is ready. So now we are producing 523, so 523. And then I can go to the output details and then output summary. Now, if I go now to the, show grid, now we will see that we have now this valve. So this valve is injecting 1.6 and it is throttling. This is the shallowest valve. This valve now is also throttling and it's injecting 0.7. This valve now is closed and obviously the last valve is closed. So we have now two valves are open. It's a condition that is not preferable, of course, okay? And the total injection rate, if you go to the, for example, system results, go to show grid and then go to nodes, then you will find now how much of these valves are injecting. So as you can see here, let's go back, sorry. Go to branch and then select column, and then you can add at the end total injection gas. This is how much you're injecting, 2.33. Okay. Now, for this one, I have two valves that are open. So I can, if I want to stay with this calculation, I can, that's fine. But let's see what will happen if I increase the injection pressure. Okay, so if I increase the injection pressure, what will happen? Am I going to inject more? And obviously, probably yes. And which valves are going to be open? Which valves are going to be closed? So, but instead of doing that, let's perform this as a sensitivity analysis. So I can go to the PT profile, and then I can select the sensitivity data to be gas lift data, and then I can select the surface injection pressure. So let us assume that we are going to vary the surface injection pressure between 1300, 1500, and 1800, and see what will happen. Click on run. Interesting. So as you can see here, we are having different behavior, and let's analyze one by one. So if I go to show grid, and now I go to the first one, when the CHP or the casing head pressure is 1300, are we really injecting? So I go to the first one, the shallowest one, because we're starting from bottom up. This is closed. This is closed. So all the valves are closed. We are not injecting anything. You see? The injection now is, we're not, the gas lift injection is poor, and that's why we're going to the original rate, right? Because there is no gas injection. There is no enough casing head pressure to open the valves. Okay? The second one is the one that we have today. But the third one is what will happen if we increase the casing head pressure or the gas lift injection pressure. So the bottom one is injecting 2.2. And now the second one is also injecting 2.2. So now we are injecting much more. All of the valves are open now. Okay. So now you can go to the system results. Sorry, the system results, show grid, and then go to branch, and then again maximum total injection rate, and you will see that we are injecting 8 when we maximize the production, the casing head pressure. So this is a very useful, and of course the reason it says 0.1 because we put 0.1 here, so we can reduce that. But what I'm trying to say is that this is I would say an advanced methodology for evaluating your gas lift system. Okay, not only you can specify a fixed injection rate. You can also add all the complexity that you want. The moment I say do not enable multi-pointing, right, I can simply run the calculation by going to the deepest injection valve. And as you can see here, I go to show grid, and you will see that, for example, here we have this valve is open, we're injecting 1.5, and then the other one we have nothing. Okay, so that's the simplest way. Okay, it will honor your rate, and then it will use this pressure to define which valve you are injecting. The more complexity you want to add is basically by enabling a multi-pointing, and there are different tasks like fixed injection pressure, fixed injection rate, or fixed both. And if you say fix both, then it will calculate a tuning factor. Of course, the tuning factor is just a multiplier, and it's not recommended. Like, for example, you say, okay, what if I want to inject only 1.5? What is the required injection pressure? Okay, then you run the PT profile again. You click on run. And it seems that the system is telling you that, the 1.5 is too low. You cannot run your system with only 1.5. So what if I tell them, okay, fine, I'm going to inject 2. No solution. Why is that? I don't know. I need to figure out why it's not honoring this this condition here. So this is enough for gas lift now. So let's talk about ESP. What if I want to design a pump for this well? So what I'm going to do now, I'm going to remove all these valves. And now again, if we run the well without anything, we get 200, right? So let's boost the production by installing a pump. So I can go easily to the ESP design. And here I have more control. I can specify how much exactly I want to produce. Like, for example, I can say I want to produce 500. And then based on that, you tell me what are the pumps that can give me this rate. So the pumps are here ordered based on the efficiency. Okay, and now if I select the first one, for example, I click OK. Now I can run the system while the pump is installed. So all that is the ESP design. And as you can see here, the pump has been installed. I can go to the actual pump performance. This is the pump head. This is how much we're producing. All right. And this is barrel per day. It's not stock tank. And this is the nodal analysis. This is, as you can see, the nodal analysis is 500. This is in stock tank. And then if I'm happy with this, because it tells you that you need 94 stages, this is a lot. But again, if I'm happy with this, I can install this pump, this ESP system. And now my ESP system is installed. I can now go and run my nodal analysis or my PT profile if you want. It's complaining about diagnostic type is not supported. Okay, well, because Let me see here. Artificial lift. We have deleted the artificial lift anyways. So let's go now again and run the nodal analysis. Why it's complaining about this? It appears that, guys, we found a bug in the system. So let me open a case with an ESP. Case studies, well simulation. So ESP simulation, this one. Now again, I'm going to run this. I'm going to remove the ESP first. Let's run the software without an ESP. The well cannot flow. Okay, obviously the outflow is higher than the inflow. So you'd like to produce maybe 3,000. So I'm going to go to ESP design. And then I'm going to tell them design production rate is 3,000. And now I'm going to select, let's say, this pump here. Okay. And run. It will calculate for me how many stages I need. We need 100 stages. And now if I'm happy with this, I click on install ESP, close, and then I run the nodal analysis or PT profile, for example. And here we go, okay? We go to the profile result, and then we see the ESP performance. This is the jump in the ESP. And if I go to show grid, I can look into the pump performance by expanding the pump row here, and it will tell you what is the speed, what is the power, surface power. Now, surface power is the same because I did not add the power correction. This is delta P across the pump, okay? And this is the Q in, Q out in barrel per day. And this is the head added across the pump, okay? We also have what we call the auxiliary results. The auxiliary results is basically, we show you the pump performance curve or the variable speed drive curve, okay? And this is for your reporting if you want to really focus on the ESP performance. So, good. So now, one last point, which I did not last, but one important point which I did not cover, which is the fluid modeling. And as you can see here in this system, the fluid here is a bit different. So let's start talking about the different fluid options in Pipesim. So what we have done so far in the previous examples is that we have used what we call the black oil. And the black oil, basically there are correlations that you use to calculate the different properties, okay? And if we really need to use more accurate or more equation of state type of fluid modeling, we can do that simply by switching into compositional. The moment I switch into the compositional, I can find that we can define components. So these are the components that are defined for my fluid, okay? We have standard components and we have user-defined components. And if I double click on the user-defined components, these are the values that are created by the user, okay? By any user. And then these are the options. So as you can see here, we have PVT packages, multi-flash, E300 and GERG. Symmetry fluid engine is coming in this year. And then you have the equation of state. You have the viscosity model, okay? Once we are done with that, we can go to the fluid. And if I double click on this fluid row here, we are going to perform the flash right away. So this is the fluid. As you can see here, this is the phase diagram, okay? Now, the flash or tuning, the flashing point right now is happening at standard conditions. So I can actually change this, and then I can calculate, this is my current condition. So I can say that, okay, if my pressure was, let's say 1000, and my temperature was, let's say 120, where am I going to be? So this is your point here, and this will show you for each of the phases what is the mixture, what is the oil, gas, and water. So you can perform automatic flash calculation by specifying the pressure and temperature here using the compositional interface. Okay, and in addition to this, once you are done with your calculation, you can actually go to the phase envelope after you run the calculation, and then you will be able to see where is your production flow path. Like, for example, as you can see here, we have the flash point. Sorry, flash point is not here. So we have the nodal analysis. So this is our system. Okay. This is the inlet condition, right? So as you can see here, this is the reservoir pressure, and then we go directly to this is the inlet of the ESP, and then we go upwards to the outlet of the ESP, and then we start going up. Okay, as you can see here, we are between this line and this line. So this is the water line, and this is the hydrate line. So we are now not crossing the hydrate temperatures, which means that there is no risk of hydrate formation. Okay. This is for compositional fluid modeling, and as I said, we can have there are two more options. One is PVT file. So PVT file, you can generate the .pvt file from other software and import it here. This is including scale chem, for example. If you want to create scale, you calculate scale deposition, or you can create a fluid file from multi-flash. The way you do that, if you have a license, you click on multi-flash file, and then you can click on plus, and now you click on new. So what this will happen, what this will do is that it will open multi-flash software user interface, and then you can from there characterize your fluid, tune it, whatever, and then select all the options. Of course, we have more options here in multi-flash user interface than we have in Pipesim. And once you're done with that, you can close it, and then the fluid will be exported back to Pipesim. Okay. Again, I mean, we don't have really time to go to all these options. Let me just finally show you an example for the network optimization. So I will go again to help, and then case studies, and then tutorial examples, and then you have is it tutorial or network optimizer. So look into this this network here. Okay, now I'm going to distribute the gas lift injection rate automatically, okay, to maximize production. Let's say we have 4 wells in our system, and then each of these 4 wells has a different gas lift injection quantity. Okay, so now let's run this network, okay, and see how much we are going to produce by using the default or the gas injection rate for each well, okay, at each well. So when I run, we see now that we have those 4 valves, okay, and if I scroll down, we have 0.67, 0.45, 0.95, and 0.73. Okay, let's go to the branches, and then under each branch, okay, we can go and say, okay, I want to see the total injection gas, and here we go. So we have, this is the total gas injection rate. Let me just copy those values and put them in Excel just to see how much total we are injecting. We're injecting 2.8, okay? So 2.8 is the total injection rate, right? And now how much are we producing? So if I go back to the node, I see that we are producing 1,848 oil, right? Now, what if I want to increase my production? Can I increase my production using the same injection gas rate? Let us see. So let's go to the network optimizer. Okay, these are the initial conditions. And now let's go to the optimization control, and we tell them, okay, maximize oil rate with the fixed injection rate of 2.8. Let's challenge the software. We are asking the software to use exactly the same total gas injection rate. However, the objective is to maximize oil production. So can it do that? Let's run. And remember, we have only 4 wells, okay? This is what is called network optimization, okay? Meaning I want to try to increase the production by honoring the total injection gas rate, okay? And obviously it was not able to increase the production, and this is because it appears that the initial conditions of my network was already optimized. So let me play with the values, because this seems that this is the final tutorial. This is the tutorial that was after optimization. So let me try now to go and using the I'm going to change the gas injection rate between the wells so that my total becomes also 2.8. So let's say that I'm going to inject here, let's say 0.5. I'm going to inject here also 0.5. And I'm going to inject here. So you have 1 now. I'm going to inject 1 here. And then the remaining is 0.8. Okay, so now let's run the network simulation now with these conditions. So we are producing 1,843. Okay, and now let's go to the network optimizer. And these are the initial conditions, reset conditions. Okay. And now we are going to tell them, okay, options. By the way, do we have any? So this is the fixed injection gas rate. Okay, maximize. Let's also maximize liquid if we can, and then we will see now the well curve parameters for the gas lift. So the minimum is 0, the maximum is 3, which is fine. And now let's okay, local constraints. Do we have any local constraints? Now we're telling him to force stable flow. So now with that, we are ready. Okay, so we are going to maximize. Okay. Why the network optimizer is not running? You see. Yeah, because I didn't specify the. So this is, I think, how much was it? Is it 300 maybe? The network simulation, how much was the C? It's 300, yes. So 300. Okay, and now we are going to use, okay, again, maximize oil, and let's run. Not a good example. There is something wrong with this model, guys. I think I apologize. It's not able to increase the production. There must be something missing in the model that I'm not aware of. I apologize for that. But this is basically the workflow, okay? And normally it works, but I need to find out why it's not increasing the production. Of course, not a good example to show in this webinar, but again, I need to find out. I think that's it when it comes to what I wanted to present in this webinar today. So let's open the floor for question and answers. And for the time being, I'll probably, let me just before that, because I'm not happy with this last example. Let me see. Do we have training exercise? Let me see here. Okay, GIS, network optimization. Let me see this one here. Okay, so now here we're probably playing with the choke settings. We're putting a constraint of maximum rate, maximum water production. We are maximizing produced gas rate. So let me just remove this constraint, optimization control. Let me just remove this constraint here. And then I'm going to run it again.